All right, so for today's lesson, I just want to do a little bit of revision on atomic structure, just so you guys can have an idea of what's going on at the particle level. So when we look at these chemical reactions, you can make the macro, which is the observations that you can see, and then talk about the micro, which is what's happening at the atomic level to justify. So first thing we got to be mindful of is the atom. When we are talking about atoms, we're talking about the smallest unit of matter. So that's the smallest that we can go down. We can't go down any further. Once we go down any further than that, we're now talking about subatomic particles. Excuse me. I'm trying to give some notes. Do you want me to write down that definition for atom? I see head shakings, yes. So an atom is the smallest unit of matter. And that's why it's so important to talk about it. In fact, the concept of an atom was first thought up by the ancient Greeks. It was an ancient Greek named Democritus that came up with this idea. So he thought about clay. I'm going to use a piece of paper for as an example. So he thought, I could split my clay in half. I can split my clay in half. I can split my clay in half. So I'm doing that with my piece of paper because I don't have clay. And you can keep splitting it in half and 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 in half. But eventually you're going to hit a point where you can't split the clay in half anymore. And that's what he came up with as the idea of an atom. So when I get to the point that I can't split the matter up anymore. So that was his first idea. And that was our first kind of concept of what makes up stuff. Now we have a better understanding of what that stuff is. And in fact, we have it listed as a periodic table of the elements. So what we have learned is that we have all these different elements that are atoms that are slightly different to each other, that can form bonds with each other to make up very complex molecules. So I passed out that pink piece of paper so you guys can have a periodic table. There's lots of information we can gather from that periodic table. The other thing I wanted to give you guys as a resource, which is on the back side, is a table of ions. So we will use both of those. And there's some other resources as well that you'll be using on this internal assessment as well. But the first thing we talk about is the periodic table and what does the different stuff in here mean. So let's start, for example, with fluorine as an atom, and let's break up what's inside and what is that information we see on that periodic table. So fluorine is number 9 right here. So let's talk about what that 9 means. Let's talk about what the 19 means. Let's also talk about what that F means as well. So I'm just going to go onto my piece of paper, and I'm just going to write out a blown up version of what we see on the periodic table for fluorine. So we see a 9 in the corner, we see an F, and we see a 19.0. So let's decode that information. There's lots of stuff that we can learn from that. All right, ready? Okay, so the F here is represents the symbol. So it's our shorthand way of saying fluorine. If I want to translate that into the name of the molecule, that's what it would be written out in the word form. And you guys have started to see the word and the symbolic form with the GIM kit and the stuff we looked at in the last couple of days with the equations. I've given you both the word equation and the symbolic equation. The symbolic equation is just based off of these symbols from the periodic table. It's a nice little shorthand for us to communicate. So, something to keep in mind on the assessment is that when we give you the periodic table, we only give you the symbols. We don't give you any of the translations. So we give you the symbol, but we don't tell you what the symbol's word is. So I want you to keep that in mind. Are we good so far? All right. Cool. The next thing to keep in mind is that there are two numbers there, and they mean two very, very different things. The smaller number is the atomic number. Trying to find some more colors because you know me, I like my colors. The larger number is the atomic mass. Keep going. Okay. So, atomic number is really useful because it gives us two bits of information. First off, that number tells me how many protons the atom has, and it also tells me how many electrons it has. So, since the atomic number for fluorine is 9, it would have 9 protons. It would also have 9 electrons. Let's see what else you might need to know on your homework. We good so far? Okay. The atomic mass tells us how much weight does that atom have, how heavy it is, how big is it. So, for this one here, the atomic mass is the number of protons plus the number of neutrons. So we can do a little bit of atomic math here. Since I noticed that my atomic mass is 19, and I know from my atomic number that the number of protons is 9, I can subtract away that 9 to figure out how many neutrons I have. Now you might be wondering, why do I only care about the protons and neutrons when it comes to mass? And that's because the electrons are super duper tiny. They are so tiny they don't even contribute to the mass of the atom. In fact, an electron's mass is about 1/8,000th of the mass of a proton or a neutron. So it's real insignificant. So we don't count it in the mass. It's barely anything. 1/8,000th. Want to write that down? You're curious? 1/8,000th, I think, is what I remember looking up ages ago. So it barely counts at all in the mass. They're super tiny. All right, let's talk about the location of where these things are. So, with our atom, the first thing we have is a nucleus. So that's in the center. Now, in order to make my life a little bit easier, I'm just gonna draw a circle to represent the nucleus. But in reality, we have to think about how there's actually 9 protons. Or should I draw it? No, I'll just keep it easy. So here's my nucleus. I have 9 protons, and I have 10 neutrons in that nucleus. Now, some things to remember. Protons are positively charged. Now, if you guys remember from electricity, The positive charges don't like to be next to each other. That's why when you have static electricity, your hair sticks up, because it has the same charge. So in order to help everything stay together like glue, we have the neutrons, which have no charge. So that's how we build together our nucleus. So I'll add those notes in there. That is my nucleus. And the protons are positive, and the neutrons have no charge. No charge, to help everything stick together. And then I'll put up here, protons, they are positive. That's my shorthand for positive. All right, keep going. All right, so we have accounted for my protons, we've accounted for my neutrons. The last thing we need to account for are the electrons. The electrons exist outside of the atom in what's known as the electron shell. You might also hear it being called orbitals or clouds as well. There's actually a lot of empty space when it comes to these electrons. Each shell has its own specific number of electrons. So do you guys, I don't know if you guys did this last year, I'm pretty sure you did. The first shell, how many electrons should it have? Just 2. So they have 2 electrons in that first shell. In the second shell, anyone want to take a guess of how many we can allow in here? 8. 8. So 1, 2, 3, 4, 5, 6, 7, 8. So 2, 4, 6. No, because I only have 9 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9. If I want to shorthand it, I would go, the electron configuration is 2 and then 7. 2 plus 7, 9 electrons. So that's where the electrons are. And they are negative. Did you guys hear about the 2882 rule? Is that ringing a bell? So when we're talking about, I'll go over it again, don't worry. I know there's some faces that are like, what? When it comes to the electron shells, each shell can hold a maximum number of electrons. The first shell can hold 2. The second shell can hold up to 8. The third shell holds 8. And then the last shell that we talk about holds 2. They're obviously more than, sorry, if I was trying to add that up, that'd be 2 plus 8, that's 10, another 8, 18, another 2, 20. But when we look at the periodic table, do we only have 20 elements? No. So this rule only works up to 20. If you want to know what the atoms look like past 20, you need to do level 3 chemistry. Are we okay so far? All right, so I'll backtrack and show you guys the general rule, and then we'll talk about the fluorine example. So when we do electron configuration, we have our nucleus. The first shell can hold 2. Next shell can hold 1, 2, 3, 4, 5, 6, 7, 8. Once I get to that 8, I move on to my next shell, which also can hold 8. And then my last shell that we talk about before it gets really complicated and have to go to level 3 chemistry is the fourth shell. So we always fill the first shell before we move on to the second shell. So it's the 2, 8, 8, 2 rule. So that's the first shell, that's the second shell, that's the third shell, that's the fourth shell. Are we okay so far? All Yes? All right. So, oh, let me zoom out a bit so you can see both. Okay. There we go. So if we look at the example that we did for fluorine, fluorine has 9 electrons. So I put the first 2 in that first shell, 1, 2, and then in my second shell, I then put the remaining 7 electrons, 1, 2, 3, 4, 5, 6, 7. I'm not going to move on to the third or fourth shell because I have run out of electrons. Are we okay with that? No. Do you need to see another example?
No. No.
He gets it? All right, I'm asking the whole class. Do you need another example? No? We're okay? This rings a bell from last year?
Yeah.
Okay, so we have half an hour left. As promised, I wanted to mainly just get down the notes on atomic structure. That was my main agenda for today. I will pass out the homework, and you'll have a choice of either using this time to work on your homework, or you can play Gimkit. All right? So you don't have to all choose the same thing.
Wait, does that mean we have to use time?
No.
Oh, okay.
Yeah. So long as you're doing some work. If I see people not working, I'm going to take some time off. You're not going to get 5 minutes added. All right? Cool.